Alright, this is now the second video for Unit 5. Unit 5 is talking about energy and matter exchange in the biosphere. And in the last video we talked about the idea that sunlight is necessary for most producers in the ecosystems of the Earth. That sunlight reaching the Earth sometimes makes it, sometimes doesn't. Sometimes it's bounced back into space by clouds. But some of it reaches the Earth. And of the stuff that reaches the Earth, some of it happens to land on plants. Plants have chloroplasts, and the chloroplasts are able to do the process of photosynthesis. And photosynthesis is what is powering all of these food chains or food webs or interrelationships between organisms. So if we're looking at energy that is going into a system, we cannot assume that all of that energy goes from one level to the next to the next. So if energy is coming in here captured by the producers, used to grow this tree, used to grow this grass or these flowers or whatever else is photosynthetic, the energy that goes to the next level is not 100%. So we have all of this energy here from here to here, all of this energy that is captured by the plants. But what is available to the next level, to the primary consumers, is less. Even if they eat every blade of grass, even if they eat the entire tree, which of course they won't, but even if they did, that level would be less. And then if we look at what's available to our secondary consumers and what's available to our tertiary consumers, it is less and less and less. So as we go through these layers, we notice that the energy seems to just be disappearing. And of course the energy isn't really disappearing, but we need to think about what's going on. We need to take a little detour into physics. In physics, one of the most important ideas is the idea of conservation of energy. The second law of thermodynamics is our key for this unit, which is transforming energy from one form to another. So from chemical to mechanical, from kinetic to potential, whatever. Anytime we make any of those changes, then some of that energy is lost. The word lost here is maybe misleading. The energy doesn't disappear. It just changes form to something unusable by us or unusable by any other life form, which could be heat. Most commonly it is heat. Big quantities of heat, if things are very hot or very cold, those are usable. But if things are just very slightly warmer than another, then that difference in heat is not going to be enough to power any processes. So this here is just looking at the laws of thermodynamics in another way. We don't need to look at it in too much detail. But in a short version, thermodynamics state that the Zeroth Law is called the Zeroth Law because it's important for the rest of the laws, but we didn't think that it was important to say until later. So the Zeroth Law of Thermodynamics, which says if you have object 2 is in contact with object 3, eventually they will reach the same temperature. And if object 1 is in contact with object 3, eventually they will reach the same temperature. And if the object 1 touches object 2 and object 3 touches object 2, then these two are also touching. Not directly, but indirectly. And so they will eventually reach the same temperature too. This is saying that all systems in the Earth, all systems in the universe are interconnected. Some of them less directly than others, but all of them at least a little bit interconnected. The first law of thermodynamics says that you cannot get new energy. You can't just make new energy. You can only transform from one form to another. The second law says that we will always lose. Efficiency will always be less than 100%. Except for in one case, and that case is at absolute zero. At absolute zero, we can do things perfectly efficiently because there is no chaos. All of the molecules have stopped moving. That's what absolute zero means. But the third law tells us that we can't reach absolute zero. The third law of thermodynamics is an interesting one because we keep trying to reach absolute zero. There are labs around the world that are trying to do this, well, maybe not today, but most days. And we keep getting closer and closer, and it would be very interesting if we were able to get to absolute zero, if we were able to stop movement of molecules. When we look at this in terms of a food chain or a food web, here this is a food chain, then we can see where this energy is being lost in biological systems. So energy coming in from the sun is being absorbed by our producers. That energy is going to be transmitted to the next level, our primary consumers or our herbivores. That energy, when those are eaten, will be transmitted to our secondary consumers. Here we only have primary and secondary consumers, and then we go straight to decomposers. When the wolf dies, of course, its body will be decomposed by bacteria or fungus or whatever in the soil. And that energy returned to the soil will be usable by those plants again. If we had perfect transfer of energy, then we would be transforming from one to the next, to the next, to the next, and then also getting energy input from the sun. And our life systems would just be more and more and more and more full of energy. But that's not true. So just in growing, that is transforming heat, light energy into chemical bonds. That cannot be done at 100% efficiency. Doing things like cellular respiration, breaking down that glucose back into CO2 and water to make ATP, cannot be done at 100% efficiency. On a hot day, a plant will do the process of transpiration, and transpiration is going to let hot water molecules evaporate into the air, which of course is going to take energy with it. If we look at the deer, that deer needs energy to move, to eat, to chew, to grow, and also it eats things that it cannot digest. So if it takes in energy, but it cannot fully harvest that energy, we would call that lost. The word lost doesn't mean it's gone. It just means not useful in this context. Same thing for the wolf. It needs to grow. It needs to power its cells. It needs to do all the stuff that living things do. It also has feces. It also has urine. It also sweats. And all of those things release energy back out into the environment, but not quite as much as went in. Then we have for our decomposers usually are warm. They create some heat. They create heat because they are not 100% efficient in their processes. So all of these steps lose little bits of energy. When we look at something called an ecosystem, we have to divide it, well, we don't have to, but we do divide it into two categories, biotic and abiotic. Biotic is living and dead. So living or once living parts of an area, and abiotic means non-living. So in this picture, biotic things, obviously the trees are biotic, the grass, the deer, the raccoon, that's all biotic, the fish. If there were a dead fish, if there were dead grass, that would all be biotic as well. Abiotic could be things like, so for abiotic, that could be things like the water. It could be things like the air. It could be things like rocks. It could be things like heat, temperature. So these things are non-living things, but they do have effects on living things. When we're going through our food chains or food webs, we often think about things in terms of trophic levels. How many steps away from the producer are they? So the first trophic level are the producers. The first trophic level gets their energy directly from the sun. The second trophic level gets its energy from the first, the third from the second, and so on. The naming system for trophic levels is really straightforward. We start with plants, they're number one, then things that eat plants, then things that eat those things, and things that eat those things, on and on. So for trophic levels, we usually have trophic levels 1 through 5. We can have trophic levels that are higher than 5, but it is rare. These guys here are the only producers. These are consumers, 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 consumers. Here are two different food chains. One food chain on the earth, terrestrial, and one in the sea, marine. So terrestrial and marine are definitely vocabulary words you need to know in this unit. So terrestrial and marine mean on earth or in the water, in the sea. We have equivalent food chains on each side. So on the terrestrial side, the producers are a plant, looks like some type of angiosperm here. The herbivore is some type of insect. The carnivore is some type of mammal. The next carnivore is a snake. And the less carnivore as a bird, but we give them names like primary producer, primary consumer, secondary consumer, tertiary consumer, and quaternary consumer. Primary being first, secondary being second, tertiary third, quaternary fourth, just like before. This naming system is just a little bit confusing because it goes primary, primary, secondary, tertiary, quaternary. So it counts 1, 1, 2, 3, 4. Because the difference between this number 1 and this number 1 is this is just the producer and this is the first level of consumer. On the marine side, the producers are called Phyto Plankton. Phyto means anything to do with plants. So really we use it for things that are photosynthetic. And plankton are things that float around in the water, things that live a planktonic life. We also have, at the next level, zooplankton. So zoo, which I know, it's written zoo, but whatever, zooplankton just means things that are like animals. I've run out of space. Animals. So zooplankton are animal-like plankton, phytoplankton are plant-like plankton, and phytoplankton are producers, because they're like plants, which are producers, and zooplankton are consumers, because they're like animals, which are consumers. As we go up to bigger and bigger fish, and eventually an orca as our quaternary consumer, the same relationships apply. Energy is transferred from energy and matter from one level to the next, but not at 100% efficiency. There's always some loss. Okay. This is a good question. I think so, because I asked it. How many trophic levels are possible? Is there a limit? So if we know that energy is being lost as we go from one level to the next, to the next, to the next, how far can we go? We can follow a rule. This rule is called the rule of 10%. And that means that as we go from one trophic level to the next, so as we're going up the trophic levels, we only get to keep 10% of the energy that was in the level below. Of course, it's not really 10% every time. That range is even greater than 5 to 20, but usually within 5 to 20, and actually usually pretty close to 10. 10% of the energy available in the previous trophic level is available for the next trophic level. So as we go up and up these trophic levels, the amount of energy is decreasing quickly. We can calculate these. To calculate them is very easy, because if we're going from one trophic level to the next, we're only keeping 10%. If we keep 10%, that's the same as multiplying by 0.1, because 0.1, of course, 10% is 0.1. So if we keep 10%, that's the same as multiply by 0.1. So every time we're going up one trophic level, we multiply by 0.1. Up one level, multiply by 0.1, which also means, of course, move the decimal one spot. So if we are going from the first trophic level to the third trophic level, so we have levels 1, 2, and 3. We're going up 1, 2 levels, which means we're going to move the decimal 1, 2 places, or multiply by 0.1 twice. So we should end up with 700 joules. If we are looking at, I'm just going to give myself some space here, the second one, the second trophic level, and we're going to the fourth. So if we have our trophic levels 1, 2, 3, and 4, from the second to the fourth, we're going up 1, 2 steps again. So if we're going up 2 steps, that means we're multiplying by 0.1 twice, which means we're moving the decimal over here twice. So we would have remaining 350 joules. I'm going to stop here.